Hello everyone. Today we're going to do a review of dynamics and forces. So what is a force? A force is a push or a pull. So a force can cause objects to move, and forces change an object's motion. For example, you could push a box and the box will begin to move. Or while a box is moving, you can push in the other direction, apply force, and the box will stop. Now, forces are measured in units of newtons. Well, there are different types of forces. Well, there's the force of gravity, the normal force, which is the force acted upon by the surface perpendicular to the plane of the surface. So if you hold a box against a wall would exert a normal force outward, perpendicular to the wall. Or if you hold it on the floor, it will exert a normal force perpendicular to the floor, which means up. Well, there's also tension, the force of tension, which we'll talk about later. The force of friction, the centripetal force, but it's not really another type of force, but that will be discussed more about later. The electric force and many other forces. Key to this unit and to the rest of physics are Newton's laws of motion. Newton's first law states that an object at rest will stay at rest, and an object in motion will keep moving with constant speed until acted upon by a net force. So if, let's say I have a book, the book will not start moving automatically. It will stay at rest, and an object in motion will stay with a constant speed. So if you're sliding, let's say, an ice cube on ice, where there's not much friction, which we'll talk about later, it will keep on sliding unless you stop it and block it with your hand, or you hit it in the other direction and its velocity will change. Now, make sure you take note net force. A net force is an unbalanced force. If you pull on a rope, let's say in tug of war, and there are two people acting with completely the same. It's the same amount of force on both sides. The rope will not move. Even though there are forces acting on, there's no net force. The forces are balanced. They all cancel each other out because they're going in different directions. Newton's second law states the acceleration of any object is directly proportional to the net force acting upon it and inversely proportional to the object's mass. Now, this law is usually written in equation form, and we'll explore that right after we talk about the third law. If you apply force to an object, that object will exert a force equal in magnitude but opposite in direction back at you. So let's say you're trying to hammer a nail in a wall. Okay, when you hit the nail with your hammer, well, of course, the hammer will exert a force on the nail, but the nail will exert the same magnitude of force but opposite in direction. So the nail will exert that same force back on the hammer. So people usually say, for every action, there's an equal and opposite reaction, and this is exactly what that reaction force is. If you hit your hand on a table, your hand will exert a force on the table, but also the table will exert a force on your hand opposite in direction. So if you hit your hand down on the table will exert a force upward on your hand. So this is the second law in equation form. Note how we said it's directly proportional to the net force. So that's this. So as the net force increases, keep in mind it's net force. Not just any force, but the sum of all the forces. That's what this weird sideways looking M thing is. That's the capital letter sigma, and it means sum. The sum of all the forces, the net force. Directly proportional to the net force. And that means, if you don't know what directly proportional means, it means if you increase the net force by some amount, you will increase the acceleration by that same amount. So let's say you double the net force. That means you double the acceleration. You quadruple the net force, you quadruple the acceleration. You cut down the net force by 1/2, you will cut down the acceleration by 1/2. However, it's inversely proportional to the object's mass, which means as the mass, if you increase the mass, you decrease the acceleration. If you double the mass, you will cut down the acceleration by 1/2. Conversely, if you halve the mass, you will double the acceleration. So if one goes up, the other goes down. Now, mass versus weight. We use them interchangeably. However, in physics, mass and weight are completely different things. Mass is a property of matter. Mass does not change even if you change location. If you're on the Earth, and let's say you weigh 50 kilograms, all right? If you go to the moon, you're still 50 kilograms. If you go to Jupiter, you're still 50 kilograms. That's your mass, does not change. Weight is the force of gravity acting on an object. Weight can change depending on whether the acceleration of gravity changes. Which means if you weigh 200 newtons on Earth, you will probably weigh about 33 newtons on the moon. Remember, weight is a force. Weight is the force of gravity. So it's measured in newtons, not kilograms. And it will change on location, depending on whether the acceleration of gravity changes. So if you've ever been on a spaceship, you will notice you will feel empty. That's weightlessness. That doesn't mean your mass is zero, because that just means your force of gravity acting on you is zero. It's simulating outer space where there is no acceleration due to gravity. And this is how you calculate weight. Fg, which is the force of gravity, also weight. M is your mass in kilograms. And G, if you don't know what G is the acceleration due to gravity, and assuming we're on Earth, it's about 9.81 meters per second squared. So here's a very simple second law problem. A 30 kilogram box is dragged along the floor by two forces. A rightward 200 Newton force and a leftward 100 Newton force. Find the acceleration of the box. So here's our solution. So our acceleration is equal to net force divided by the mass. That's just the second law. And keep in mind, some students will probably try to solve the second law for both the right force and the left force, but that just gives you two different accelerations, and that cannot happen. It's the net force. So we're going to treat left as negative and right as positive by convention. So FR, we'll do right, minus FL, so left force, divided by M, equals 200 newtons minus 100 newtons divided by 30 kilograms. And that gives us an acceleration of 3.33 meters per second squared. All right, tension. Tension is the force a rope or string exerts on an object. It is always a pulling force. You cannot push with a rope. You can pull with a rope, however. It's always a pulling force. You can solve problems the same way you can solve any other force problem, second law. However, you should first draw what's called a free body diagram. These diagrams shows all the forces on an object and can help you break up your forces into their components and make solving problems easier. So what I've shown here are some examples of free body diagrams. So Here's some examples of free body diagrams. This one, so it's probably someone pushing a box, on a floor. So you have force of gravity, mg, so that's the force of gravity. We have N or Fn, so they used N, the normal force acting from the surface, perpendicular to the surface, so it's probably horizontal, and your horizontal applied force, F. Over here, although it should have went outward like this, they decided to write it like this, but it shows all the forces acting on it. That means it can easily show you the net force. We're going to move to this one here. It's probably another person pulling a box and trying to oppose friction, F frict. So FF, it's the applied force, you can see by the longer arrow, is greater than the friction force, so it'll probably be accelerating to the right. And again, it'll show you the net force, so you can see the net force will probably point to the right. Because friction, the arrow is smaller than this applied force. Now, we can easily see the normal force and the gravitational force, they both balance out. They have about the same length. They have the same length. That means they cancel out. So this one is the harder one. We have two free body diagrams. The one for the signal, the traffic light, and the one for the point where all three ropes attached. So we have Fg, the force of gravity acting on the traffic light, and we have tension 3 acting upward. Now on this support, like this connection point, we have tension 3 acting downward. However, we have tension 2 and tension 1 acting upward. Now, so we're going to assume that this is completely still. That means this and this have to cancel. Like their horizontal component and their vertical component must cancel. So this and this will cancel, and this will cancel as well. So we're asked to find, so here's a practice problem. It's sort of tricky, but if you know how to draw a free body diagram, it should help you. So we're asked to find the tensions T1, T2, and T3. And we have a 5 kilogram bowling ball, and it's attached to a rope with tension T3. Then these two ropes, they're attached, they have tensions T1 and T2 respectively, and they're also hung at angles of 40 degrees and 50 degrees. So here's a solution. So I've drawn a very quick free body diagram here. Okay. So what I'm going to do is I'm going to draw this free body diagram very quick. I drew here. So what we're going to do is divide these into their respective forces. So this is T2x, and this is T2y. All right, this is T2x and T2y. T2 to 2y. Oh, I'm sorry, that's T1x. That's T1x. All right, that's T2x and T1x. That must cancel. This is T1y, T1y, and T2y. I'm sorry for the confusion. However, it's resolved. So that's T1x, that's T1y, and this is T2y. All right, so this is 40. It's 40. Sorry if you hear the weird clicking sounds, that's my computer. I'm trying to draw these. So that's 40, that's 50. Now these horizontals, they're parallel. That means this is 40. This is also 40. This is 50. By the alternate interior angles theorem, this is 40, this is 40, this is 50, this is 50. Okay, so now that we've done this, let's start our problem. Let us start our problem. Oh, I erased it. Okay, that's bad. However, just draw it again. Okay, so I drew the entire thing again, and now I know how not to stop the draw thing because I know now it doesn't save. So we've seen 40, 40, 50, 50. These are both parallel. I divided T2 and T1 to its components. So the net force must be equal 0. There's no acceleration. The mass is completely still, and everything's completely still. So if we look at our first one, well, I didn't draw a free body diagram, but it's quite simple. T3 minus mg equals 0. Look at the free body diagram. It will just be mg pointing down and T3 pointing up on the ball. Now that equals 0. So we're going to isolate T3 using algebra. T3 equals mg equals 5 kilograms times 9.81 meters per second squared equals 49.1 newtons. Now we're going to focus on this free body diagram here. Now you might be thinking, why is T3 pointing down? Why is T3 pointing down? So T3 was pointing up because it was holding the mass up, the 5 kilogram mass up. However, here it will burden this support. It will pull it down because the mass is pulling it down. And however, T3 will stay the same. The third law. It will action reaction. This and the first one that was pointing up would be the same magnitude. So we don't need to worry about that. So we have T1 sine of 40 plus T2 sine of 50 minus T3 equals 0. So that's T1y plus T2y minus T3 equals 0. They all must add up to 0. So I just solved. I just add T3 here. However, we can't really do anything with this. Both T1 and T2 are unknown, so we can't really, so we have to rely on our x direction. So we have T2 cosine, so T2 cosine of 50 minus T1 cosine of 40 equals 0. So that's x. So this is T2 cosine 50 minus T1 cosine 40 equals 0. So I'm going to solve. So I'm going to add T1 cosine of 40 to both sides. We get T2 cosine of 50 equals T1 cosine of 40 equal to T1 cosine of 40. So I'm going to solve for T2 by dividing both sides by cosine of 50. So we get T2 equals 2 T1 cosine of 40 divided by cosine of 50. Okay, so what I did here was I substituted this. Over here. Substituted this right over here. Oh, I'm sorry. I substituted this right in here. I'm sorry about that. Substitute it over here, right in here. So I changed this to numerical values just to make it more clean. So forget this bottom one. So that's not the equation I substituted. It was this one right over here. Substitute right in there. So you have 0.6428 T1, that's sine of 40 degrees, plus, well, I put cosine of 40 divided by cosine of 50 times the sine of 50. That got me 0.9130 T1 equals 49.1 newtons, which is the tension we got from T3. So I added these together, 1.8346 T1 equals 49.1 newtons. So I got T1 equals 31.56 newtons. So I'm going to input this right in here. I have to be careful where I'm drawing my arrows. Right in here. So we get T2 equals 31.56 newtons times cosine of 40 divided by cosine of 50. We have T2 equals 37.61 newtons. Okay. So I'm just going to let you just grasp that in, how we solve this problem, and then we'll move on to the next one. Sorry. Okay, so I'm going to remove everything because that's what this does. Now we're going to go to the next one. Friction. Friction is the force opposing motion. The force of friction is always in the direction opposite the object's motion. So if you push a book to the right, friction will oppose you and it'll be directed to the left. However, if you push the book to the left, friction will go to the right. So it will always oppose you. There are two types of friction, static friction and kinetic friction. There are also other types of friction, but these are the two we'll deal with in the forces unit, static and kinetic. Static friction keeps objects from moving in the first place. So the reason why a book will just stay there is because static friction will just keep it, will hold on to it. If you try to push a huge bookcase, you might think, hey, I'm applying a force and there seems to be nothing else applying a force. Why isn't it moving? There is. Static friction will keep objects from moving. It's the force of static friction, and that's what's keeping the bookcase still. Kinetic friction is the one that is more often known as friction. It opposes motion and slows an object down. So if you threw a book across a carpet, so I just slid a book across a carpet, it will slow down because kinetic friction has a net force on, has the net force. The force of friction is the net force. Sorry. So here are the equations for friction. So FF, the top one, will be the equation for kinetic friction. It is equal to mu. That's the Greek letter mu. This number is known as the coefficient of friction. It is usually below 1. However, there's some that are above 1. So that's mu. It's a coefficient of friction. It depends on what material. The material of the object and the material of the surface times the normal force, F sub n. And the bottom one is this force of static friction is less than or equal to mu sub s, the coefficient of static friction, times F sub n. You might wonder why there is this less than or equal to sign. That's because there's no a set value. This formula gives you the maximum value of static friction this surface can apply. Once it surpasses this number, this force, then static friction will give away to kinetic friction. And also keep in mind, these two numbers are different. Mu k and mu s are different. Mu s is usually always larger than mu k. So This less than or equal sign, back to the less than or equal sign. This is because you can just apply very light force to a bookcase, and static friction will only apply a light force back to keep the bookcase in equilibrium. Or you could really push on the bookcase and still not have it moving because the force of static friction will have the same force just in the opposite direction. So this static friction force can change. That's why there's a less than or equal to sign. But once you have a force greater than mu s times Fn, then static friction gives away, the box will start moving. However, kinetic friction will start to oppose your motion. However, it's just a little bit easier than actually trying to get it to move in the first place. So here's a quick practice problem. A 10-kilogram block slides across the table with a speed of 5 meters per second. If mu k, that means coefficient of kinetic friction, is 0.4, how far will the block move before stopping? Okay, so they already gave us a free body diagram, so that's helpful. And we know V is equal to 5 meters per second. So what we can do is we can find the acceleration using the second law, net sigma F over m, and the only net force, because they're just letting it go, so the only net force acting on the block is the friction force. That in turn equals mu k times Fn, and since we're on a horizontal surface, the normal force will equal mg, or the weight. So we can just sub in mg for here. The m's will cancel, and this is a symbolic expression for acceleration. So what I did is I went to this kinematic equation. So remember from kinematics, this equation, Vf squared equals V naught squared plus 2a delta x. So I just solved for delta x. I subtracted V naught squared and divided by 2a. Then I just subbed in this mu kg in for a. So this is the final symbolic expression. So if you actually do all the math, you will get 0 meters per second squared minus 5 meters per second squared divided by 2 times 0.4 times negative 9.81, because it's opposing your motion, meters per second squared, and that will be equal to 3.186 meters. So it will slide for 3.186 meters before it finally stops. Now, inclined planes, this is a confusing topic, but it is easy to understand if you know how to draw a good free body diagram. So the equations are the same, but there is trig involved. First, rotate the coordinate axes. So I'm going to have to set it on draw mode. So I'm going to rotate these axes. So this is the x-axis, and this is the y-axis. I just rotated it so the x-axis is parallel to the plane, and the y-axis is perpendicular to the plane, the surface of the plane. So once we have this coordinate system established, in these coordinates, mg is an angled force. In our normal coordinates, it is not. However, in these coordinates, it is. So you can break it up into components. So here, this is equal to theta. This is equal to this. So that's equal to theta. So if you go and actually prove it, that's equal to theta, this is equal to 90 minus theta, since this is a right angle, 90 minus theta. And notice, this and this are parallel. So this must also equal 90 minus theta. And since the components are always complementary Since these angles are always complementary, since you're breaking up into perpendicular components, this angle will equal theta. So you can, then you can immediately see that this, the perpendicular component, will be mg cosine of theta, and this parallel component will be mg sine theta. So the x component will be mg sine theta, the y component will be mg cosine of theta. All right, I'm gonna just let you take that in. Okay, so here's our first practice problem. So a skier is skiing down a snowy incline with an angle of 25 degrees. If the skier's mass is 50 kilograms and the coefficient of kinetic friction is mu k equals 0.2, find the acceleration of the skier. So just application of Newton's second law. This equation is really important, especially in this unit and all your other units in physics afterwards. It's just one of the most important equations. So it's used almost every problem. Now the net force will be the parallel component of gravity will be this. Looks like weight with a little parallel sign. So your parallel component of gravity minus friction. So I just mu k times mg cosine theta. You could always derive this because friction is the kinetic friction is mu k times Fn. Then over here you see n, they use n, is balanced out by mg cosine theta, or weight perpendicular. Seems to look like weight perpendicular, so that's mg cosine theta. So you could just substitute that in, since the normal force and mg cosine theta balance out, that means they have the same magnitude, so you can substitute that in. So what I did was I factored out the m. That means this m and this m cancel out. That means that will equal to g times sine theta minus mu k times g cosine theta. And if you really want to factor out the g, you get g times the quantity sine theta minus mu k cosine theta. So if you substitute all our given values in, you get 9.81 meters per second squared times the quantity sine of 25 minus 0.2 cosine of 25, and that gives you about 2.37 meters per second squared. So that will be the acceleration of your skier. So now we're going to move on to multiple block systems. You can have systems of objects moving sort of together, and this may seem daunting, especially if you look at the diagrams. However, you can just use Newton's second law, and it works exactly the same way. So two masses, m1, that equals 20 kilograms, and m2 equals 30 kilograms, are connected by a light string and attached to a light frictionless pulley. However, there is friction on the 30-degree incline, with mu k equaling 0.3. Find the acceleration of the masses. So if you actually want to draw the forces, put draw mode back on. So we have F and 1. This is M1G. This is the parallel and perpendicular component, x or y component. And this will be equal to, they use alpha. So that's M1G cosine theta. Then we have M1G sine theta. sine theta, sorry, alpha, but who cares? It's just an angle. And we have tension pulling us back. Tension pulling us back. All right, sorry for that interruption. I just had a problem with my computer. So where were we? Yes, we were drawing T. So tension will be pulling us back. So what direction will friction go? Well, M2 is heavier than M1. So this will be going upward, up the incline. That means this will be friction. It's not as large as I just drew it. I just needed to distinguish the arrows. Now for M2, we have M2G. Then we have T right here. This T and this T have the exact same value. It's just Newton's second law. M2G will be pulling on M1. Sorry, M2 will be pulling on M1. M1 will be pulling on M2. So by Newton's third law, sorry, did I say second law? By Newton's third law, these tensions will be the same. Okay, I'll just let you grasp that. Okay. Now, the hard part is actually solving it. So the first way you can do it is basically make two equations, one for M1, one for M2. So I chose upward and down the incline as positive. So I have M1A, so that's, net force equals M1A, so I put M1A equals M1G sine theta plus mu K times M1G cosine theta minus T. So that's just if you look at the net forces in the x direction. So we have our second equation for M2, a little less complicated. It's just negative M2G plus T. Now, it's a system, and you can easily eliminate T. So plus T minus T, they both go away, and we end up with M1 plus M2A equals M1G sine theta plus mu K M1G cosine theta minus M2G. So if you don't know what we did, we just added these two equations together. So M1A plus M2A, we could just factor out A, and that's how we got M1 plus M2 times A. So if we solve for A, we get M1G sine theta plus mu K M1G cosine theta minus M2G divided by M1 plus M2. And we substitute all those numbers in, we get a final acceleration of negative 2.90 meters per second squared. This negative means the acceleration is opposite the direction we chose. So the blocks will move up the incline and down. So M2 will be powering our acceleration and will be accelerating downward at acceleration of 2.90 times 2.90 meters per second squared. Now, that was exhausting, and if you actually want to do an easier way, it's just a formula. So I'm going to try using this formula. So the acceleration of the entire system, because remember, I didn't point this out, the acceleration is the same for both blocks. So M1 in the last example will accelerate at the same 2.90 times 2.90 meters per second squared, and M2 will also accelerate at 2.90 meters per second squared. So the acceleration of the entire system equals net external force. So an external force is basically a force that only acts on one block. The internal force is tension. So we don't need to include that, because if you actually look here, it's the basis for the equation, the tensions will cancel mainly due to the third law and little elimination, the internal forces will cancel out. So the forces that only act on one block will be the external forces divided by the total mass of the system. And that's shown right here and right here. So we had a 20 kilogram block and a 30 kilogram block. So the total mass you would put here will be 50 kilograms. So here's another practice problem. Two blocks, one of mass 4 kilograms and the other mass 8 kilograms are attached by a light string. You pull it down the 30-degree incline with a force of 80 newtons. So find the tension in the cord. So if you want to find the tension in the cord, first, we're going to use our new formula here. It will hopefully make things very easy for us. So we have our F external. So that's mg sine theta. So if you want to do it this way, I put m1 plus m2 g sine theta because they will all accelerate the same rate down the incline. However, you want to do m1 g sine theta plus m2 g sine theta. They're both in the same direction. So that is what allows you to factor out this g sine theta. Then we're going to add the applied force of 80 newtons, so F applied or F app, divide by m1 plus m2, the total mass. So you could just cancel out, you could separate and cancel, so that equals g sine theta plus the applied force divided by m1 plus m2, and we can get the acceleration equals 9.81 meters per second squared times the sine of 30 degrees plus 80 newtons divided by the total mass, 4 kilograms plus 8 kilograms, and that equals 11.57 meters per second squared. So we're not done, we just found the acceleration. So if you want to find the tension, what we do here is we apply the second law to only one block. We're going to choose this one because it has the least amount of forces. Well, they don't have the least amount of forces, but all the forces act in the same direction, so it makes it easier to keep track of the signs. So we have t plus m2g sine theta equals m2a. And if we solve for t, we get m2a minus m2g sine theta. And you can factor m2 out if you want. Then you just plug in the numbers and you get a tension of 53.3 newtons. And I think we are done. We just reviewed all of forces in less than 45 minutes. Even if you feel confused, if there's one thing to take away from this, it's signs, the signs, drawing a good free body diagram, and knowing the second law inside and out.